Welcome to our chapter on exponential and logarithmic functions. This is a big part of the Math 3-1 course, so we're going to go through a lot of examples explaining exponential functions, logarithmic functions, the laws of logarithms, and then solving exponential and logarithmic equations. We'll start with an exploration of some basic exponential equations. Solving an equation means to find the values of x which make the equation true. In the case of an exponential equation, our unknowns are in the exponent. Typically, we use logarithms to bring the unknowns out of the exponent down into the coefficient position before solving. However, we can avoid using logarithms in cases where both sides of the equation can be written using the same base. Let's look at this example of 4 to the 2x equals 8 to the 2x minus 3. Because both sides of the equation can be written using a base 2, we will replace 4 with 2 squared and 8 with 2 cubed, and then we will simplify using our exponent laws. We multiply the 2 by 2x to get an exponent of 4x on the left side, and we multiply 3 by 2x minus 3 to get 6x minus 9 on the right side. Because both sides have the same base and are equivalent, we can conclude that the exponent of the left side must be equal to the exponent of the right side. There's not really a logarithmic step that was taken here. This is just a logical deduction. If 2 to the something is equal to 2 to the something else, then the something and something else must be equal. So we can say now that 4x equals 6x minus 9. We subtract 6x from either side, and then divide both sides by negative 2 to find our answer of x equals 9/2. Let's review how to solve an exponential equation graphically using our calculators. We'll use the same equation as in the previous example. By typing 4 to the 2x as the y1 function and 8 to the 2x minus 3 as the y2 function, we can find the solution by determining the point of intersection, and specifically its x-intercept. This is because if there's a point of intersection, that means at a certain x value, both sides of the equation will output the same value. This means the left side and right side are equal, and our equation has been satisfied. So, the x-coordinate of the point of intersection is the solution to the equation. Here we see that the point of intersection happens when x is 4.5. That is equivalent to 9/2. Another option is to input y1 as 4 to the 2x minus 8 to the 2x minus 3. This is as though we have set up the initial equation to be equal to 0. In this case, rather than determining the point of intersection, we will find an x-intercept by calculating a 0 of the function. Finally, we could verify this numerically by simply typing in the left and right expressions using 4.5 or 9/2 in place of x. We should see that both expressions output the same value and can conclude that 4.5 or 9/2 is therefore the solution. Class example 1 asks us to solve an exponential equation algebraically and then to verify graphically. Let's have a look at this equation. 1/3 to the x minus 2 equals 27 to the 2x times 9 to the x plus 3. Well, what stands out to me is that we have bases of 1/3, 27, and 9. These are not the same base, but I recognize all of these as powers of 3. So I'm going to rewrite each as 3 to the something. Let's start there. Note that 1/3 is equivalent to 3 to the negative 1. Now, the second step is very important. Here, we have applied a power of a power law in order to distribute the exponents of negative 1 and 2 into their binomial exponents that are outside of the bracket. So for example, 3 to the negative 1 to the power of x minus 2 has generated an exponent of negative x and positive 2. On the right side of the equation, we have 3 cubed to the 2x, which gives us 3 to the 6x, and we have 3 squared to the x plus 3, which gives us 3 to the 2x plus 6. I walk through this because our brain is now in this multiplying mode, but in the next step we have to be careful not to multiply. When we have two powers of the same base that are multiplied together, our exponent laws tell us to add the exponents. So we must very carefully add the 6x and the 2x plus 6. Now that we've done this correctly, let me tell you that what I see most often is students in the previous step drop the bases and immediately equate the exponents. This is going to happen now that we have 3 to the x 3 to the x plus 2 equals 3 to the 8x plus 6, but only because we have a single power term on either side of the equal sign. Once we've determined that negative x plus 2, the exponent from the left, and 8x plus 6, the exponent from the right, must be equivalent, the algebraic steps here are not very complicated. Add x to either side, subtract 6 from either side, then divide by 9. But I again want to point out that had we dropped the bases at an earlier step, it would have been incorrect to write that negative x plus 2 was equal to 6x times 2x plus 6. So be careful about that step. To verify graphically, be sure to type the original expression from the left side of the equation and the original expression from the right side of the equation in as y1 and y2. Then we will calculate the intersection point, and the answer to our question will be the x coordinate of that intersection point. Alternatively, we could say that the left side of the equation minus the right side of the equation would equal 0, and so if we type it all in as y1, then we would calculate the 0 of the function. Though both of these methods give us the same answer, it's worth noting that in the first, our point of intersection may have a y-coordinate that is out of our window. And for some students, this can be problematic because they want to see the intersection point. Remember, in order to calculate an intersection point, the x value must lie within the given domain of your window, but you don't actually need to be able to see the intersection point. So I encourage students to not waste time fiddling with the window settings. However, if that does bother you, then using the second method here, where you're finding the 0 of the function, is advantageous because you know you'll always be finding an x-intercept, so it will always be in the window of your calculator. When we first started learning about powers, we treated them as repeated multiplications. So, If you had 3 to the power of 4, for example, that meant 3 times 3 times 3 times 3. The base of 3 was repeated 4 times. Well, essentially that's no different with an exponential function. We're now saying y equals b to the x. We're setting b as the value of the base, and then our x value represents all the possible exponents. However, we will often work with bases that are larger than 1 or less than 1, and to distinguish between these is really important. So if we're repeating a multiplication of a number that is larger than 1, then we are increasing the value of something each time. One way to think of this is that the value of 1 is equivalent to 100%. So to multiply something by more than 100% is to increase its value. And to multiply by a value that is less than 1, though still positive, so for example 0.7 or 0.45 or 1/2, would be to multiply by something that is less than 100%, which means we are decreasing in value. So if our base is greater than 1, our graph, as it moves from left to right, will increase. And if we have a base between 0 and 1, our graph, as we move from left to right, will be decreasing. It's important to note that the base cannot be a negative number, that it cannot be 0, and it cannot be 1. Some properties of the exponential function that are true in all cases are that the domain will be all real numbers. And in cases where we do not have a vertical displacement or a k value, the range will be greater than 0 when the coefficient is positive, and will be less than 0 when the coefficient is negative. This is maybe the first time we've seen a horizontal asymptote. So the graph is approaching but not actually reaching the x-intercept. The x-axis. This means we'll have no x-intercept. Again, that changes once we have a k value. If we do not have a coefficient in front of our base, then our y-intercept will be 1. This is because, regardless of what the base value is, when we put the exponent as 0, it will always output a height of 1. Keeping in mind that the base of an exponential function cannot be negative, 0, or 1, let's look at the different exponential functions in the cases where the base is greater than 1 and when the base is between 0 and 1. Now, even though the base cannot actually be 1, if we picture the graph of y equals 1 to the x, it'll help us see a progression as we increase the value of the base. Y equals 1 to the x is a horizontal line. Regardless of what value is put in place of x, it will always output a height of 1. Well, if we replace this 1 with 1.1, we'll see a graph that is now climbing, but it's going to climb slowly relative to other bases. So what would it look like if instead of 1.1, it was 1.5? Well, that graph is going to climb more steeply. And what if instead of 1.5, it was 2, or 4, or 10? What we see is the greater the value, but more specifically, the further that value is from 1, the steeper the graph. If we now look at the graph that is falling from left to right, which is when our bases are between 0 and 1, what we see is if we took a base of 0.9, so y equals 0.9 to the x, we have a base that is less than 1, but only a little bit less than 1. So it would start a bit above that y equals 1 to the x line and fall quite slowly. But as we change the base to 2/3, which is 0.67, or 1/2, which is 0.5, or 1/4, which is 0.25, as we make the base smaller and smaller and smaller, we actually see a graph that falls quite steeply. This is because the further the base value is away from 1, the further that curve will be away from the line 1 equals x. So the steeper the curve. This is enough to help us picture our graph and distinguish between two cases where the bases are different in value. In Math 30-1, we tend to associate our transformations with parameters. Here, we're going to look at the effect of a vertical stretch, on our exponential function. Note that a can also represent a reflection in the x-axis. Earlier, we stated that an exponential function would have a y-intercept of 1, because in the equation of y equals b to the x, regardless of the b value, if x is replaced with 0, b to the 0 evaluates to give 1. However, if we have a coefficient of a in front of b to the x, because that a is not affected by the exponent of x, when we replace x with 0, b to the 0 still evaluates to give 1, but then multiplies by a. So now, when x equals 0, our output value is a, so our y-intercept is at a. Notice in the three examples shown to the right that when the a value is 5, the y-intercept is 5. When the a value is 2, the y-intercept is 2. And in the original example, we have an invisible coefficient of 1 appearing before 2 to the x, and so our y-intercept is 1. This intercept would change if we introduced a horizontal or vertical displacement. However, in the absence of that, it is always true that the y-intercept of an exponential function is the a value. In working with an exponential function, the k value represents a vertical translation, just as it always has for us. However, when we first learned about vertical translations, it was probably in the context of quadratic functions or parabolas. And with a parabola, we usually determine the vertical translation by observing the behavior of the vertex. Now, because the vertex starts on 0, 0, wherever it ends up will show the value of k in terms of the y-coordinate of that vertex. Well, this isn't exactly the same with an exponential function because an exponential function doesn't have a vertex, and because it has no points on the x-axis, there's no point that is unaffected by a stretch. Why am I saying all this? I'm saying this because if you have an a value other than 1, then it's not necessarily easy to determine how the y-intercept has moved, or it's a multi-step process anyway. So when we look at an exponential function, in order to determine the k value, we're not going to look at any of the points that are on the graph. We're going to look at the horizontal asymptote, which is a collection of points that are not on the graph. However, the horizontal asymptote of an exponential function in an untransformed case will sit on the x-axis. So if that horizontal asymptote is anywhere but the x-axis, that reveals our k value. Long story short, we can think of the k value as being the distance between the x-axis and the horizontal asymptote. Because our a value was representing our y-intercept before the vertical translation, we can kind of think of the a value as being the distance from the horizontal asymptote to the y-intercept. In the example we've shown here, we have a positive a value, meaning the graph is moving up or is rising from left to right, and is above the horizontal asymptote. So we would say that the horizontal asymptote is at a height of k, and that the y-intercept is at a height of a plus k. When an exponential function has a negative a value, there has been a reflection in the x-axis. Because our horizontal asymptote sits on the x-axis, and because this reflection would happen before any vertical translation, we may say that the graph has been reflected in the horizontal asymptote. Note, if we have reflected our graph in the horizontal asymptote, then our range, which would otherwise be y is greater than k, the horizontal asymptote's height, is now y less than k. It's worthwhile to discuss this reflection in the context of an x-intercept. An exponential function typically doesn't have an x-intercept. However, there are two cases in which it will. If the graph has a positive a value, meaning it is above the horizontal asymptote, then if we shift the graph down, it will now cross the x-axis and have an x-intercept. Or, if our a value is negative and our exponential function's graph lies below the horizontal asymptote, then if our k value is positive and we move the graph up, it will cross the x-intercept. In the case where a and k are both positive, or a and k are both negative, there will be no x-intercept. Class example 2 asks us to find the equation of an exponential function given a graph and a few details. We're told that the equation will take the form y equals a times b to the x plus k. So it's important for us to know what we can find from the graph here and what we'll need to find algebraically. Well, we're told there is a y-intercept at 0 and negative 7.5, and that the x-intercept and horizontal asymptote have integer values, so positive or negative counting numbers. This means that if we see that dot at approximately negative 2, 0, we can confirm that is actually at negative 2. And our horizontal asymptote, which appears to be at negative 8, is actually at negative 8. That's what that information is saying, have integer values. The first thing we know is that our horizontal asymptote will give us our k value. So we can replace our k with a negative 8. Now, of a and b, what can we take from this graph? Recall that our a value represents the distance from the horizontal asymptote to the y-intercept. So if we have a y-intercept at negative 7.5, that means it is 0.5 above the horizontal asymptote of negative 8. This is enough to determine that our a value is positive 0.5. At this point, we have taken an equation that had y and x, so two variables, and a, b, and k, three parameters, and we've replaced two of the parameters, so now we have only one unknown parameter of b. Our default strategy across many units in this situation is to pick a point on the graph and use it in place of x and y. That will allow us to solve for the single unknown parameter. Notice that subbing in a point when we still had a and b or b and k as unknowns would not have allowed us to solve for b. We can use the point negative 2 and 0 to replace x and y in our equation. Now we need to isolate b. Most students are comfortable adding 8 to both sides and then multiplying by 2 or dividing by 0.5. This gets us to the step of b to the negative 2 equals 16. So what to do next? Well, in order to isolate b, we want b to have an exponent of positive 1. So when we raise each side to the same power, then our exponent laws tell us we will multiply the current exponent of negative 2 by whatever the new power is. This allows us to introduce the power, in this case negative 1/2, which is the reciprocal or flip of negative 2. Because when we multiply a number by its reciprocal, we generate a product of 1. So by putting both sides to the power of negative 1/2, we've achieved b to the power of 1. On the right side, this leaves us with 16 to the negative 1/2, but that is something we can evaluate either by hand or with a calculator. Because the square root of 16 is 4, and because 4 to the negative 1 would be 1/4, we find that 16 to the negative 1/2 is 1/4. So, we have now determined the values of a, b, and k and write them in the equation. Notice, x and y are variables. We weren't trying to find the value of x and y, so in our final equation, we should be writing y and x again. It's a great habit to develop to type this determined equation into your calculator and confirm that its graph gives the same thing as you'd seen in the original question. Notice I set the window settings to be between -6 and +6, and -9 and +8 to match what I was given in the original question. My exponential curve looks like the one given, and I feel confident in my answer. I won't talk through every step of this worked example because I think it's important to be able to learn from other people's written work. However, I do want to draw your attention to just two parts of this question. Here we've been given a function and asked to describe different characteristics of it and then sketch a graph of that. I just want to highlight over and over and over that when we're asked about intercepts, when finding a y-intercept, we replace x with 0, and an x-intercept, we replace y with 0. Too often I see students determine this graphically, but these are actually really easy algebraic questions to do. So again, to find a y-intercept, replace x with 0 and evaluate. To find an x-intercept, replace y with 0 and solve for x. Class example 3 asks us to sketch an exponential function by first determining the coordinates of the x and y intercepts and also drawing attention to the asymptote. We will then state the domain and range of our function. Recall that to find a y-intercept, we will replace x with 0. So here we will find f of 0. It is important to pay attention to our second step. After we have replaced x with 0, we have y equals 2 times 3 to the 0 minus 18. Recall that exponent of 0 does not apply to the 2. Also recall that in our order of operations, we have to evaluate an exponent prior to a multiplication. So the first thing we evaluate is 3 to the 0 is 1. Then we multiply by the 2. This gives us 2 minus 18, so a y-intercept of -16. In the case of the x-intercept, we will replace y with 0. Now we have an equation where the unknown is in the exponent. This is an exponential equation, which in many cases will require us to use logarithms. However, if we are able to write both sides of the equation using the same base, we can avoid logarithms. Let's first isolate our power term. As a first step, we added 18 to either side. Then we divided by 2. So now our single power term of 3 to the x is equivalent to 9. Because 9 is a power of 3, we can rewrite it as 3 squared. So if 3 to the 2 equals 3 to the x, we can conclude that x has a value of 2. This has found our x-intercept at 2 and 0. As discussed earlier, the k value of the graph represents the height of the horizontal asymptote. So in our function f of x equals 2 times 3 to the x minus 18, we can take the -18 to be our horizontal asymptote. Because our a value, in this case 2, is positive, our graph will lie above the horizontal asymptote. There is no interpretation required in writing the domain here. Any exponential function will have a domain of all real numbers. However, to determine the range, we must first determine the k value, in this case negative 18, and then determine if the graph lies above it or below it. Again, a positive a value means we're above the graph, so here y is greater than negative 18. Let's now discuss the logarithmic function. We'll start by viewing this in terms of its relationship to the exponential function. So in an exponential function, our independent variable, or our input, our x, is an exponent on a given base. And then the output value, the dependent variable, or y, is the resulting value of the power. So just to clarify, the exponent is the little number raised above the 2, and the power is 2 to that exponent, in what it turns out to be. So for example, in 2 to the 3, I would say that the exponent is 3, and the value of the power is 8. So that's an exponential function. A logarithmic function will ask the question backwards. So we're going to know the value of the power, and we're going to ask what was the exponent. So you'll often hear people say that a logarithm is really an exponent. Well, anytime we ask a question in the opposite direction, we're kind of changing the input and the output. So we're saying, instead of knowing this input and getting that output, I'm going to know the output and ask for the input. And this relates back to our inverses. So if you recall from transformations, an inverse was when we changed or interchanged the domain and the range. We changed all things x and y, and we observed a reflection over the line y equals x. So that's kind of our context here as we start looking at the logarithmic function as an inverse. We'll start with an exponential function y equals 2 to the x. It could have been 3 to the x or 5 to the x, but this is just an example. So y equals 2 to the x. We'll see that all the points on this graph have as their x-coordinate what the exponent would be, and then have a y-coordinate that corresponds to 2 to that exponent. So for example, 2 to the power of 3 gives 8, 2 to the power of 2 gives 4, 2 to the power of 1 gives 2, and then on the negative side I see 2 to the negative 3 would give positive 1/8, and 2 to the negative 2 would give positive 1/4. If I were to interchange x and y and write this as a function x equals 2 to the y, that would mean I'd be asking the question differently. So now I would say 8 equals 2 to the what? And the answer would be 3. 4 equals 2 to the what? And the answer would be 2. 2 equals 2 to the what? And the answer would be 1. And then in the negative side, and now I mean negative as in below the x-axis. So 1/8 would be 2 to the what? And the answer would be negative 3. So we can see that we have generated an inverse, which is a reflection over the line y equals x. And when we look at the characteristics of these two graphs, we'll see how they've changed. Our blue graph, the exponential one, had a domain of all real numbers, as exponential functions do, and had a range greater than 0. This is saying all values above the horizontal asymptote. Well, with our logarithmic function, our domain will be all positive values, so to the right of the vertical asymptote, and the range will be all values of y, all real numbers. Note how this domain and range relate to the domain and range of the exponential function. Also, notice that where the exponential function had a horizontal asymptote on the x-axis, which is the line y equals 0, our logarithmic function will have a vertical asymptote on the y-axis, which is x equals 0. Now, it's not typical for us to write equations in terms of x equals. So how can we take the inverse, which is x equals 2 to the y, and write it in the form y equals. Okay, well, if x equals 2 to the y, that means we're inputting the value of the power, and we're asking as the output for what the exponent was. So we read this as y is the exponent on a base of 2 that would generate x. And so we need some way of representing is the exponent of base 2 to get. And we use the word log. And so when we see y equals log, and then as a subscript that 2, and then in the brackets x, we read it as log base 2 of x. And it means y is the exponent on 2 that generates the given value of x, which we call the argument of the logarithm. Many students are used to graphing with their graphing calculator, but most graphing calculators are not able to accept inputs in terms of x equals. A big advantage of Desmos graphing software, which is available at desmos.com/calculator, is that you can type functions in terms of y equals or x equals. And here, y equals 2 to the x and x equals 2 to the y, not surprisingly, show themselves as inverses. Well, if instead of typing x equals 2 to the y, we type y equals log base 2 of x, we actually see the same graph as we did before. So I should note that y equals 2 to the x is, or has as its inverse, x equals 2 to the y, and y equals 2 to the x also has as its inverse, y equals log base 2 of x. This means that y equals log base 2 of x and x equals 2 to the y are equivalent. They are not inverses, they are equivalent. Again, the logarithmic function is the inverse of an exponential function. So with an exponential function, we are given as our input the value of the exponent, and our output is the evaluated value of the power. But with a logarithmic function, our input is the evaluated value of a power, and the output is the exponent that had generated it. So we see an inverse graph, meaning a reflection over the line y equals x, exchanging all things domain and range. And in the equation, after changing x and y, we will learn how to convert from exponential form into logarithmic form by effectively dropping the base into a logarithmic notation. Much like with exponential functions, we will differentiate between cases where the base is greater than 1 and where the base is between 0 and 1. Just like the exponential function, we will not have a base of 1, nor will we have a base of 0, nor a base of any negative number. So the easiest way to start thinking about the logarithmic function is still as an inverse of the exponential. So if we remember that exponential functions with a base greater than 1 rose as we went from left to right, and that exponential functions with a base between 0 and 1 were falling as we went from left to right, then we can imagine what the inverse graph would look like. So in both cases, there will be a y-intercept of 1 that becomes an x-intercept of 1, but you can see how the reflections of the graph look a little bit different here. With a logarithmic graph, we're starting down in quadrant 4, and as we move right, it's actually moving up into quadrant 1, whereas in the base between 0 and 1, we're starting up in quadrant 1 and falling down into quadrant 4. There are some occasions in math when we can avoid writing a value because it's implied. Think of the term x. I mean, we don't need to write the coefficient of 1, and we don't need to write the exponent of 1. It's not wrong if we do. Well, with logarithms, we need to know the base, but we don't always write it in the case where the base is 10. We call these common logarithms, and it's just because we work so commonly in base 10 that if it's not written, it's assumed the base is 10. In future math courses, you may discover natural logarithms. Here, instead of writing log, L-O-G, we write ln, L-N. This implies a base of e, which is a number that has a lot of applications in math. But we won't be doing that in this course. So for now, you just need to know if you see log without a base written, that there is an implied base of 10. Let's look at how to convert equations between exponential and logarithmic form. This is a strategy commonly used when we need to find the value of an exponent and we can't write the two expressions in terms of the same base. So in the examples shown here, which are 4 to the x equals 1/64th and 10 to the x equals 1/100th, we are actually able to write both sides in the same base. But we're still going to use these examples to see how we would convert to logarithmic form for cases where we couldn't do that. In order for this to work, it's important to understand what the word log or logarithm is meaning here. And I like to think of it as a question. Logarithm is saying, what exponent would I put on the given base to generate the output value shown? So, in the case of example A, where we're given 4 to the x equals 1/64th, or 1/64, I would be saying, what is the exponent that goes on the base of 4 to generate 1/64th? And then the answer to my question would actually be the exponent. This will always be the case, and is the reason most teachers say that a logarithm is an exponent. So notice, the logarithmic term is equal to the value of the exponent. Now, it's tricky to read sometimes if this is relatively new to you, as we work with exponents and fractions and bases. But the word logarithm is in the same vertical alignment as that x is. The 1/64th, if it were not a fraction, would be in that same alignment, but that base of 4 is a dropped subscript. So it's important that you sort of write things in the proper position on the page. So let's try this with our example B. What exponent would go on 10 to generate 0.01? The answer is the exponent of x. Let's read that again. What exponent, that's the word log, would go on the base of 10, there's our subscript, to generate an output of 0.01. That's our argument, the value we've put in the brackets. And the answer will be the exponent, in this case x. Recall that here, because the base is 10, I could also write this without writing in the base of 10. Just a couple of notes regarding this worked example. First, an important thing to check is that when you convert between exponential and logarithmic form, or vice versa, the base always remains the base. So if I look at example A, I have a logarithm with a base of 3. When I convert this to my exponential form, the base of the exponent should be a 3. Also, reminder that the output of a logarithm is the exponent. So here, the x that was answering the question, what exponent goes on 3 to generate 243, should appear as the exponent on that base of 3. I also wanted to point out, looking at example B, that as a reminder, our base and our argument can never be 0, nor can they be negative. However, there's nothing stopping an exponent from being negative. So it's okay for this output value here to be -4. But the 1/2, which is of course itself not a variable, and the x, those two positions can never be 0 or negative. In class example 5, we'll convert logarithmic equations into exponential form in order to solve them. Remember, a logarithm has a base, an argument, and an output value, which is the exponent. So when we rewrite it in exponential form, the base will be the base, and the output will be the exponent, and that argument will be the output of the exponential function. So in the case of log base 1/3 of x equal to -3, the 1/3 becomes the base of the exponent. The -3, the answer to the logarithm, becomes the exponent, and the argument, that x, becomes the output. At this point, we can evaluate 1/3 to the -3. Well, a negative exponent means to take the reciprocal, or the flip of the base, so 1/3 becomes 3/1. And that's just like 3. So 3 cubed is equal to 27. In part B, we see 1/2 equal to log base x of 5. Again, the base of the logarithm will be the base of the exponent. Recall that the answer or output of a logarithmic equation is the exponent of the exponential. So this becomes x to the 1/2 equal to 5. How will we solve this? Well, remember that we want to end up with a statement that says x equals something, which means x to the 1. So we need to perform an operation such that the exponent of 1/2 becomes an exponent of 1. To make 1/2 become 1, we would need to multiply it by 2. Because it's in the position of the exponent, to multiply the exponent is really to raise that side, or that power, to a power of 2. So we'll put both sides to the power of 2 to maintain the equivalence. So x to the 1/2 equals 5 becomes x to the 1 equals 5 squared. And 5 squared is to give 25. In example C, we'll see that converting between log base 16 of 2√8 equals x and its exponential form takes the base of 16 and gives it the exponent of x. But you also want to note here that I've rewritten 8, which was the square root of 8, as 8 to the 1/2. In general, we want to avoid having radicals in our exponential and logarithmic equations, because radicals can be written with rational exponents, and that will always be more helpful as we work in this unit. Now, it's important also to see in part C that we're converting into from logarithmic into exponential form because the question's asked to, and it will be both good practice and helpful in this case. However, example C was already solved insofar as x was isolated. So this is really an example where we could just evaluate log base 16 of 2√8. But because we haven't reviewed how to do that yet, let's stick with this method. So log base 16 of 2√8 is the same as log base 16 of 2 times 8 to the 1/2. And so that is the same as 16 to the x equals 2 times 8 to the 1/2. We recognize that 16, 2, and 8 are all powers of 2. So we rewrite 16 and 8 as 2 to the 4 and 2 to the 3. There's a critical difference between the, say, second and third step, or third and fourth step, depending on how you're reading this. As we go from 2, let's say where it says 2 cubed to the 1/2, in that step to the next one, we are multiplying the exponents because we have the power of a power. So the 4 multiplied the x, and the 3 multiplied the 1/2. 3 times 1/2 equals 3/2. However, in the following step, where we had 2 to the 1 times 2 to the 3/2, This is not the power of power, this is the product of two powers, which means 2 to the 1 times 2 to the 3 halves requires us to add the exponents, not multiply them. So now we have to resolve 1 plus 3 halves by generating common denominators. Because 1 is equivalent to 2 halves, 1 plus 3 halves makes 5 halves. And now we have 2 to the 4x equals 2 to the 5 halves. So we can conclude that the two exponents must be equivalent. Dividing both sides is like multiplying both denominators by 4. So on the left, we end up with x, and on the right side, 5 over 2 times 4 is 5/8. Let's see how we could check these with our calculator. In part A, we could put the left side of the equation as y1 and the right side of the equation as y2. Notice some calculators have a log base function, meaning you can input bases other than 10. For those who don't, we have to use a different notation. Log base 1/3 of x will be typed in as log of x over log of 1/3. We'll talk more about why this is so later, but for now, just take it and move on. So here we have log base 1/3 of x as y1 and negative 3 as y2. We need to find the intersection point of these two functions. However, the problem is the intersection point is outside of the default window of negative 10 to positive 10. We know this because we already know the answer is going to be 27. In this example, I've changed the window up to an x maximum of 30, but that's only because I knew the answer already. In a case where the answer was not known to me, I recommend to students that if you don't see the answer going from negative 10 to positive 10, jump all the way up to 100 as the next x maximum. There's no reason to make small incremental increases in your guess, because you can always make the window smaller again once you've seen the intersection point. Let's try some more complicated examples now. We're again going to convert from logarithmic form to exponential form in order to solve these logarithmic equations. A common theme we'll see as we try to convert between logarithmic and exponential form is that we need to isolate the log term, or sometimes the power term, before converting. So here, while I have the coefficient of 3, I'm not able to convert my equation to exponential form. To get rid of it, I simply divide both sides by 3, and now it reads log base 5 of 2x equals to negative 1/3. So my base of 5 will become my base for the exponent, and the answer of my logarithm, that negative 1/3, will become the exponent on 5. Now that I have 5 to the negative 1/3 equals 2x, I see that I'm trying to solve for x. So I'll divide both sides by 2. In this case, we are going to leave the answer in that form. Of course, there are other things we could do. We could, for example, move 5 to the negative 1/3 into the denominator. We could write it as the cube root of 5 at that point. But none of this is going to make it any easier for us to type in our calculator. And since we've noted the nearest hundredth here, we'll just type it in now. So 5 to the negative 1/3 divided by 2 gives us 0.29. In example E, we're asked to solve log base 3 of the tangent of x equals 1/2. Ho ho ho, here's some excitement. We have a logarithm and a tangent in the same question. Well, no problem. What you need to see here is that tan x is within the brackets, so that is the argument. So for now, we have log base 3 of the argument of tan x equals 1/2. Let's not be distracted by the tangent. We're going to convert from logarithmic to exponential form by taking the base of 3 and assigning it the exponent of 1/2. So 3 to the 1/2 is equal to tan x. I said a few slides ago that in this unit we want to avoid radicals, but here I think it's going to be helpful for you if we rewrite 3 to the 1/2 as a square root of 3. Do you recall your work with trigonometric ratios and where the tangent of x was equal to the square root of 3? Well, this question's asking for on a domain between 0 and 2 pi. So we're going to answer in radians, but let's first think this through. Where is tangent positive, and what reference angle has a tan ratio of root 3? In case you're rusty with radians, the arctan of root 3 would give us 60 degrees. That is equivalent to 180 divided by 3, so we can write it as pi over 3. But this is not our complete answer. This is only the reference angle. Which rotational angles have a reference angle of 60 degrees, or 1/3 of pi, and generate a positive tan ratio? Many students will be familiar with the cast rule. This is a helpful way to remember in which quadrants which ratios are positive. Tangent is positive in quadrant 1 because both the x and y coordinates are positive, which is to say the opposite and adjacent sides. And tangent is positive in quadrant 3 where both the x and y values are negative, so opposite over adjacent is negative over negative. So we can determine that our rotational angles are 60 degrees in quadrant 1 and 180 plus 60 degrees, which gives 240 degrees in quadrant 3. Converting these into radians, we see that we have 1/3 of pi and 4/3 of pi. Part F, we have the logarithm base x of 1/16 equals to negative 4/3. So as we convert this, our base of x will be the base for the exponential, and the negative 4/3, the output of the log, will be our exponent. So we have x to the negative 4/3 equals 1/16. Again, when we solve for x, we want the final step to read x equals. So I need this exponent to become 1. What do I do to negative 4/3 to make it become positive 1? Well, my easiest option is to multiply it by its reciprocal, negative 3/4. So I need to raise both sides to the same power of negative 3/4. On the right side, I now have to evaluate 1/16 to the negative 3/4. Now, it's important to understand what the different parts of this exponent are doing. A negative sign is flipping the 1/16 to be 16. The 3 is cubing it, and the 4 is taking the 4th root. Importantly, in Math 20 we learned when we take an even indexed root, so a square root, or a 4th root, or a 6th root, or an 8th root, we must consider both the positive and negative root. So here, while our calculator will only spit out the answer of 8, we need to consider both 8 and negative 8. However, because x in this example represents a base on a logarithm, we know that the base and the argument for a logarithm cannot be 0, nor can they be negative. So we will see negative 8 as a possible answer, but we will in fact reject it. The only answer to this question is x equals 8. Let's look at some of the characteristics of a transformed logarithmic function. First, we'll talk through the worked example, and then we'll go through one step by step. Here we see the function f of x equals log base 3 of 2x plus 3. Now, in order to determine the domain, we'll also be finding the vertical asymptote at the same time. Because the domain of a logarithm is related to its argument, which is the part in the brackets, the 2x plus 3, and the fact that that argument must be positive. So it can't be 0 and it can't be less than 0. So we write that 2x plus 3 must be greater than 0, and then we're going to work to isolate x. We subtract 3 from both sides and then divide by 2 to find that x must be greater than negative 3 halves, or negative 1.5. Well, on the graph, that negative 1.5 is the value that would make the argument 0, and so that's where we're going to see our vertical asymptote, when x is equal to negative 3 halves. And so that's that vertical dotted red line. And because our domain says that x must be greater than that, our graph will only appear on the right side of that vertical asymptote. Now, in order to find some points to plot, we will think about the x and y-intercept here. In the case of the y-intercept, we replace x with 0 and evaluate the right side. And to find the x-intercept, we replace y with 0 and then convert to exponential form in order to solve for x. So we'll go through that step by step on the next slide, but just wanted to give an overall idea of how these graphs are constructed. Remember that the exponential function had a domain of all real numbers, and now that we're working with logarithmic functions, which are the inverses of exponentials, we see that the range is all the real numbers. In class example 6, we are given the graph of f of x equals log base 2 of 5 minus 2x. And we're asked to add some details that we're going to determine algebraically. So let's start by figuring out the domain and range of this graph, and then talk about the asymptotes and intercepts. A critical feature of logarithmic functions is that their arguments must be positive. So here we have in the brackets 5 minus 2x, and that expression must be greater than 0, not equal to, strictly greater than. So we write 5 minus 2x is greater than 0. As we solve for this, there's one of two things we could do as a first step. Here, I've shown adding 2x to either side. Now, the other option would be to subtract 5 from each side, but that's going to make one thing very different. If you have a coefficient that is negative, when you divide through, you must change the direction of the inequality. So in the case that I've shown here, we'll be dividing by positive 2, which will not change the direction of the greater than symbol. But if we'd written negative 2x greater than negative 5, we would have to divide through by negative 2, and that would change the direction. So just be aware of that. Here we see that 5 halves must be greater than x, or x must be less than 5 halves, meaning our graph is left of a vertical asymptote that will be found at x equals 5 over 2, or 2.5. We know that the range of every logarithmic function will be all real numbers. It is the inverse of an exponential, which has an unlimited domain, and so no surprise here, no restrictions on the range. Recall that because a logarithmic function has a vertical asymptote, it happens where the argument would be equal to 0. In this case, 5 minus 2x is 0 when x is 2.5, or 5 halves. And so just like we found as our limit of our domain, the 5 over 2 will be the x-coordinate of our vertical asymptote. In order to find an x-intercept, we must replace our y with a value of 0. Here, we have 0 equals to log base 2 of 5 minus 2x, and so we convert this into exponential form by putting the 2 that is the base as the base under 0, the exponent. So we get 2 to the 0 equals 5 minus 2x. 2 to the 0 is 1, and now we'll work to isolate the x. This means that when y is 0, x is 2, that is our x-intercept. Finding a y-intercept is as simple as replacing x with 0 and evaluating. Here, we'll leave the log base 2 of 5 as an exact value, knowing that it's a little bit greater than 2. And that's our graph. In section 3.3, we learn about the laws of logarithms. These laws are used to help us simplify or expand logarithmic expressions as needed. The first two log laws we see, the product and the quotient, are typically used to write multiple logarithmic terms as a single one, or to expand a single logarithmic term into multiple terms. Our third log law is used to move the coefficient into the exponent position or the exponent into the coefficient position. This can allow us to rewrite expressions so that we can combine them into a single logarithmic term, or sometimes is used so that we can evaluate parts of a logarithmic expression. We'll look at several examples of these, but first, let's discuss our change of base identity. Our change of base identity allows us to rewrite a logarithmic expression using a different base, provided we use the same base in both the numerator and denominator. So the log base b of argument c can be written as the log of c over the log of b as long as we assign the same base to both of those logarithms. This can be really helpful for one of two reasons. One, it can allow us to evaluate and find exact values even without using a calculator. Or two, it can allow us to evaluate with a calculator expressions that we might not otherwise be able to, depending on the version of your calculator. As an example, we can write log base 4 of 64 as log base 2 of 64 over log base 2 of 4. Now, this is not particularly needed in this example because log base 4 of 64 is already something we can evaluate without a calculator. But we're using this example so that you can see how both are equivalent. 2 to the power of 6 is 64. That means the exponent that goes on 2 to make 64 would be 6. And so log base 2 of 64 would be equal to 6. Similarly, log base 2 of 4 would be equal to 2 because that's the exponent on 2 that makes it equal to 4. So this expression is equal to 6 over 2, which is equal to 3. We could also have written log base 4 of 64 as log base 8 of 64 over log base 8 of 4. This one might be a little bit less helpful because though it's probably obvious to you that log base 8 of 64 is 2, it might be less obvious what the values of log base 8 of 4 is. In order for 8 to become 4, we would have to square it to 64 and then cube root it down to 4. This means the power on 8 would be 2/3. So this expression becomes 2 over 2/3, which is also equivalent to 3. So already we've shown two examples using different bases that show the potential of the change of base identity. Now, the real reason we like this change of base identity is so that we can use our calculator. Some people have a calculator that allows you to type in a log base. For example, here, by pressing Math and choosing the option A, I can type log base and insert the 4 as my base to type log base 4 of 64 and a value to give 3. But if I couldn't, I could type log 64 divide by log 4, and my calculator would assume the base of both expressions to be 10. This would then still output a value of 3. Your calculator has two default log buttons. The first is log, for which the default base is 10, and the second is ln, which is the natural logarithm using a base of e. At this stage in your math, you may not have heard much about e, but e is a very important number, especially in calculus, with a value of approximately 2.718. You should have an e button somewhere on your calculator if you want to check. Now, this goes a bit beyond the Math 30-1 curriculum into Math 31, so we'll just leave the conversation there. As mentioned, some calculators don't have the log base function. This means that you can't specify a base other than 10 when typing it in. It may be that yours is one of these and you didn't know that you've been using the change of identity base all along. So let's say you want to type in log base 4 of 64 in your calculator. Well, you may have to type log of 64 divided by log of 4. In this case, you're using the change of base identity by assigning a base of 10 to both the numerator and the denominator. But you'll still get the same answer as if you typed log base 4 of 64. Sometimes a problem will require us to make use of multiple logarithmic laws. Here we see an expression with three terms. Two of them have coefficients, so first we'll have to raise those coefficients as powers. Then, because some of the terms are positive and some are negative, we'll have to use both the product law and the quotient law. Notice that the 3 in front of the log base 2 of 6 becomes the exponent on the 6 in the next step, and the 2 in front of log base 2 of 18 becomes the exponent on 18. Then, because there are two positive terms and one negative term, we see two factors in the numerator, the 12 and the 6 cubed, and one factor in the denominator, the 18 squared. 12 times 6 cubed divided by 18 squared becomes 8, and now our logarithmic term is much simpler. The log base 2 of 8 is 3 because 2 cubed equals 8. Let's go through a couple more examples and try this together. Here are two examples in which we'll combine terms into a single logarithmic term before evaluating. On the left we see log 40 plus log 500 minus log 2. The fact that the bases aren't written means that they are base 10. Since they're all the same base, we can combine these terms. The first two terms are positive, so the arguments of 40 and 500 go into the numerator as factors multiplying together. The last term is negative, so its argument of 2 goes in the denominator. And then we simplify 40 times 500 divided by 2, which makes 10,000. We can consider what exponent goes on a base of 10 to make an output of 10,000, and the result is 4. This means that the log of 10,000 is 4. In part B, we first have to treat the coefficients of 1/2 and 2 by raising them as exponents of the arguments. Now that we have the 1/2 as an exponent on 144 and the 2 as an exponent on the 3, we can combine these terms. Students sometimes make the error of reading this as the argument of the first divided by the argument of the second times the argument of the third, meaning they put both the 4 and the 3 squared in the denominator. We want to identify each term as being positive or negative, and then, according to that, place its argument in the top or bottom. So because log base 3 of 144 to the half was a positive term, and log base 3 of 3 squared was a positive term, those two arguments appear in the numerator. We can evaluate the square root of 144 to be 12, multiply that by 3 squared, which is 9, to give 108, and divide by 4 to get 27. Then we can ask ourselves, what exponent goes on 3 to give a result of 27? The exponent would be 3. In class example 8, we will again combine multiple logarithmic terms together into a single term expression. As a first step, we will raise all of our coefficients as exponents and distribute the negative sign into both terms of the bracket. This gives us log of a squared plus log of c to the 1/3 minus log of c squared plus log of b cubed. Once we've identified which terms are positive, we will put the arguments of those terms in the numerator of our single-termed log expression. This means that a squared, c to the 1/3, and b cubed go in the numerator, while the c squared goes in the denominator. Note, even though the logarithmic expressions were added in the previous step, we are multiplying the arguments together. This follows our log law and also represents the fact that when exponents, i.e. logarithmic terms, are added together, that represents the powers, which are the arguments, being multiplied together. Our next step requires us to simplify c to the 1/3 over c squared, two powers in that fraction that have a common base. Now it might seem like an error to have written c to the 2 minus 1/3 in the bottom, but let's think about this for a second. When we have a fraction in which the power in the numerator and the power in the denominator are of the same base, and the numerator has a larger power, well, we subtract and we write the result in the numerator. But when we have the same base in the numerator and the denominator, and it is the denominator with the bigger exponent, if we do a subtraction of top exponent minus bottom exponent, we get a negative result, which then requires us to move it to the denominator and change the sign. Well, effectively, that's what we've done here. We have moved the c to the 1/3 into the denominator as a first step, and then added the positive 2 and the negative 1/3 together within the denominator. By rewriting 2 as 6/3, we can subtract 2 minus 1/3 to give us 5/3. This means that the simplified expression is the log base 10 of a squared b cubed over c to the 5/3. The worked example shown on this slide asks us to express the log base 3 of 1800 as an equivalent expression using m and n, which have been assigned the values of log base 3 of 2 and log base 3 of 5 respectively. This style of question can appear a little bit confusing at first, but with some practice, we see that the strategy is generally the same. Here, we're going to take the argument of 1800 and we're going to break it down into a factorization. Not necessarily a prime factorization, but perhaps a prime factorization. Our goal is to rewrite 1800 using factors of 2 and 5, and then any number that can be written as a base of 3. The reason for this is anything that is written using a base 2 will be able to express in terms of m, and anything written with a base 5 will be able to express with a base of n, and then anything written in terms of base 3 will be able to evaluate as a constant term. So we take our calculator and we divide 1800 by 2 as many times as we can, and then we divide it by 5 as many times as we can, and then we hope the number we have left over is divisible by 3. Specifically is a power of 3. So here we find that 1800 is equivalent to 2 cubed times 5 squared times 3 squared, or 9. And so we rewrite 1800 as this factorization. So log base 3 of 2 cubed times 5 squared times 9, which we then separate into 3 separate logarithmic terms. Log base 3 of 2 cubed plus log base 3 of 5 squared plus log base 3 of 9. And in this moment, we have to be really careful to not replace log base 3 of 2 with m and log base 3 of 5 with m yet. The reason being, the exponent of 3 and 2, which appear on the arguments of 2 and 5, they don't apply to the full logarithmic term. They only apply to the argument. And so right now we don't actually have log base 3 of 2 cubed. We have log base 3 of 2 cubed. But once we move that 3 down in front, now we have 3 times log base 3 of 2. And log base 3 of 2 is what was equal to the value of m. So now that we've dropped the exponents down, we replace m and n, and we evaluate the last term, log base 3 of 9, to be 2. Wow, that was a lot to follow. Let's work through some more examples to sort of get more comfortable with this. In class example 9, we are asked to use our log laws and the assigned value of k equal to log 17 to write equivalent expressions for 2 logarithmic terms. In the first case, we're given the log of 170. So we want to factor 170 in terms of powers of 17 and powers of 10. 17 because of our given value of k, and 10 because of the base of our logarithm. In this example, we quite quickly find that 170 is simply 17 times 10, and we split this into 2 logarithmic terms using our log laws. We're able to replace log 17 with k, and we can evaluate the log of 10 to be 1. This other expression is quickly checked in our calculator by checking log 170 and then log 17 plus 1. Because they give the same decimal value, we feel very confident in our answer. In part B, let's first remember that we don't use roots a lot in this unit, and so it's more productive to rewrite them as exponents, rational ones. So here the square root of 17/100ths is the same as saying 0.17 to the power of 1/2. In our next step, we'll change that decimal of 0.17 into its fraction form of 17/100ths before bringing the exponent down as coefficient. Now remember, a division in the argument of a logarithm represents the subtraction of 2 logarithmic terms. So the log of 17 over 100 is the same as saying the log of 17 minus the log of 100. Notice we've bracketed this because the coefficient of 1/2 has to apply to both of the terms. Again, we can replace log 17 with k, and we can evaluate the log of 100 because it's a base of 10. Here we end up with 1/2 times k minus 2, which is equivalent to 1/2 k minus 1. This is another expression that we can check quite easily in our graphing calculator. Class example 10 is much like our last 2 examples. So let's take a second to recognize the first step every time. We are given a logarithmic term, in this case log base 2 of 405/16. And then we're given a and b, which are equal to some exact values. In this case, log base 2 of 3 and log base 2 of 5. The arguments of 3 and 5 and the base of 2 signals that you need as a first step to rewrite that 405/16 in terms of powers of 2, 3, and 5. Once we've done this, we see that 405 is equal to 3 to the power of 4 times 5. We also know that 16 is 2 to the power of 4. Because this is a division, we'll rewrite it as a subtraction of 2 logarithmic terms, and then we'll replace the 405 with a 3 to the 4 times 5. It doesn't really matter if you replace 16 with 2 to the 4 or just directly evaluate it to know that 4 would be the exponent that would go on that 2 to make 16. The log base 2 of 16 turns out to be 4. So now we split the argument of 3 to the 4 and 5 into 2 terms. So log base 2 of 3 to the 4 plus log base 2 of 5. Recall, though we can replace the log base 2 of 5 in this step with b, we can't replace our a yet because that 4 doesn't apply to the whole logarithmic term, it only applies to the argument. so we need to bring it down as a coefficient before making our substitution. Now we see a explicitly in the first term and b explicitly in the second term, and can write our final expression. In class example 11, we'll continue to use log laws to evaluate expressions. However, these ones will be a little bit different. I'll show you a second way to solve them, which might appeal to you. So in the first example, we're told that log base 5 of x is equal to 2, and then we're asked to evaluate an expression which contains that, but sort of trapped within it. So log base 5 of x cubed over 25. Seeing the division in the argument, we know we can rewrite this as a subtraction of two logarithmic terms. The number one error we want to avoid is replacing log base 5 of x with 2 prior to dropping that exponent. That exponent of 3 does not apply to all of log base 5 of x, but only to the argument of x. So it's not until we drop it as the coefficient of 3 that we can make our replacement. Our second term, log base 5 of 25, is something we can evaluate using our knowledge of logarithms. So now we get 3 times 2 minus 2, which is simply 4. Returning to the original question, we were told that if log base 5 of x is equal to 2, what would the other one be worth? Well, log base 5 of x equal to 2 is logarithmic form, but if we converted that to exponential form, it would say x equals 5 squared. So we can simply replace the x in the second expression with 5 squared, and then it becomes log base 5 of 5 squared cubed divided by 25. And our calculator will tell us that that evaluates to give 4. In our second problem, we have log base 3 of 9 times ab squared. In a situation where we're told that log base 3 of a is equal to 6 and log base 3 of b is equal to 5. So we can split this into 3 separate logarithmic terms and then try to make replacements in each one. Again, we have an exponent that needs to be dropped before we can do so, so we bring down the 2 on the b squared as coefficient. We evaluate log base 3 of 9 to give 2, and are told that log base 3 of a is 6, and log base 3 of b is 5. This means we have 2 plus 6 plus 2 times 5. Again, we can confirm this result by going back to our original question. If log base 3 of a is equal to 6, then a is equal to 3 to the power of 6, or 729. And log base 3 of b is equal to 5, so b is equal to 3 to the power of 5, or 243. Replacing those in our logarithmic expression allows us to evaluate and find an answer of 18. Let's get to the fun stuff. Class example 12. Here we're given an equation and we're asked to rewrite it in order to isolate m. Now I encourage you to pause this and give this a try on your own first. This is a challenging question, and if it weren't a multiple choice example, it would be really tough to know when to stop. However, because we have some options, you might be able to figure this out on your own. First, because we know that we'll be isolating m, we want to get it alone. Usually, when we have logarithmic expressions, we raise all of the coefficients as exponents. That's a good idea here, and will actually help us a lot. What we see is, as that 2 goes up to square the 3 root m, the 3 becomes a 9, but importantly, the root sign over the m is cancelled out. So now we have log base 3 of 9m equals n plus log base 3 of p cubed. When we solve logarithmic equations, our habit is typically to put all the log terms on one side and the non-log terms on the other. Then we can reduce the multiple log terms into a single log term, and that usually makes converting a lot easier. So here, we've got log base 3 of 9m minus log base 3 of p cubed. The subtraction of two logarithmic terms because it becomes a division of their arguments. So we end up with the log base 3 of 9m divided by p cubed. This is equal to n. Well, we still need to isolate m. So now we want to convert that left side out of logarithmic form. We do that by taking its base, the 3, and raising it under the n, which now becomes the exponent. So this converts into 3 to the n equal to the argument of our original logarithmic expression, 9m over p cubed. We multiply both sides by p cubed and divide by 9. And typically this is where we would stop. But when we look at our multiple choice examples, we see that this answer is not there. All of them have the p cubed in a numerator position or a multiplying position. So we want to look at how this 3 to the n over 9 is showing up. The secret here is to rewrite 9 as 3 squared. This will allow us to use our exponent laws to subtract 3 to the n and 3 to the 2 exponents, making it 3 to the n minus 2 times p cubed. Certainly one of the more challenging examples we've seen so far. Earlier in this chapter, we talked about solving exponential equations by writing the powers on both sides using the same base. Here we see an example 2 to the power of x minus 1 equals to 1/8. It might not be obvious on first glance, but both 2 and 1/8 are powers of 2. Because of this, we can write both sides as base 2 and then just set the two exponents equal to one another. This is a great way to solve exponential equations when we can. However, in the vast majority of cases, we will not have two powers that can be written using the same base, and so we will be required to use logarithms. This isn't much more difficult, but there are two different cases to look at, which we'll see coming up. Broadly speaking, there are two main strategies for solving exponential equations. The first is to introduce logarithms to both sides of the equation. This can be a little bit messier, having more logs in the equation, but is also more flexible, as it allows us to solve equations where we have multiple power terms of different bases. The cleaner version, which is sometimes less flexible, is to isolate a single power term and then convert the equation into logarithmic form. This allows us to bring an unknown down from the exponent and then isolate it to find its value. We'll walk through both of these examples, and you can decide which one you're most comfortable with. Once we have our answer, note that there are a couple ways we can verify it. The first and most straightforward is to just type the numerical value we got back into the original equation for the left side and right side and confirm that they give the same value. The second would be to take the original equation and type the left side as your y1 function and the right side as your y2 function. By determining the intersection point of these, you have found the x value that satisfies and therefore solves the equation. This can take a bit more practice as you need to understand how to adjust windows and find that intersection point, but is also the most accurate way. In class example 13, we will solve an exponential equation twice. In one case, we will isolate the power term and convert to logarithmic form, and in the other, we will log both sides. In both cases, we want to recognize that the reason we're using logarithms is because our unknown is in the exponent. So a common theme that we'll start with is the idea of isolating the power term. Here, the 1/5 out in front is a coefficient, whereas the 1.2 is actually the base of the power. So in order to convert to logarithmic form, we must first isolate the power of 1.2 to 2x plus 1, and we do that by multiplying both sides by 5. This cancels out the 1/5 on the left side and gives us the right side equal to 15. When we convert to log form, the base of the exponent becomes the base of the logarithm, and the exponent itself, the 2x plus 1, becomes the answer to the logarithm. So that 15 is our argument. So we end up with log base 1.2 of 15 equals 2x plus 1. Now, this is no different from equations you would have solved in grade 7, except that now we have the presence of this log base 1.2 of 15 distracting us. Nonetheless, to isolate x, we will simply subtract 1 and divide by 2. At this point, we'll need our calculator, and then we'll round to the nearest hundredth. We find an answer of x equals 6.93. We'll verify this later. In our second method, instead of converting from power form to logarithmic form, let's introduce a logarithm to both sides. Here, we are performing the same operation and therefore have maintained the equivalence. Our laws of logarithms allow us to bring the exponent down as a coefficient. Notice the use of brackets here. The 2x plus 1 will be distributed to the log 1.2. So we end up with 2x times log 1.2 and 1 times log 1.2 equal to log 15. Now, you might think this looks like a really complicated equation, but in essence, we just have a bunch of terms and one of them has an x in it. So what we want to do is subtract away the log 1.2 from both sides so that the term with the x is the only one on the left side, and then we'll divide every factor that is not x. So by dividing both sides by 2 log 1.2, we have now isolated our x. Again, we'll make use of our calculator to evaluate this and find the same answer of 6.93. In order to model exponential growth or decay, we have one formula, and it's rather simple. Y equals a times b to the power of t over p. In this, a is our initial value. B is our base of the power, which is the factor of growth or decay, effectively. And then t is our elapsed time, and p is our period. For most people, the value of a is relatively straightforward. There's some confusion between t and p, and b is straightforward in some examples and awkward in others. Let's start with the idea of b representing the factor of a doubling period. Well, when I say the word doubling, most people naturally think of a 2. No problem. If I said tripling, most people naturally think of a 3. No problem. But then we use this word half-life, and half-life is rather confusing as a word, but it really just means the halving period. So when we talk about a half-life or halving period, that means the value of b is 1/2 or 0.5. And it also represents the period of time it takes for a population to decay to 1/2 its initial amount. So half-life is actually the value of p, but it informs the value of b as being 1/2 or 0.5. Let's see if we can get a better understanding of this as we look at some examples. Let's use class example 14 to see how we can model an exponential decay situation with a half-life. Here, we have a situation showing a decay curve for a radioactive substance. We can see from the graph that the initial population count is 80. I won't pretend to understand a lot about radioactive substances and what exactly we're counting, but that's not really important here. What is important is we start at a quantity of 80. 2 days later, our quantity has diminished to 40. 40 is half of 80, so we can determine that 2 days is the half-life of this radioactive substance. In our formula, this allows us to do 3 things. Replace the initial value of A with 80, the B value with 0.5 or 1/2, and the P value with 2. Now, in part B, we're asked to use our equation to predict how long it would take for the amount to decay to 1.5 counts per minute. This is our final amount, and it goes in the position of the dependent variable, y. So it is on the left side of the equation. We see 1.5 equal to. Now we have an equation in exponential form, and in order to solve it, we're going to need logarithms. We know this because our unknown value is t, and it's found in the exponent. So remember, when the unknown is in the exponent, we use logs to solve. Remember that our first step is always to isolate the power term, so we divide both sides by the coefficient of 80. Now we can convert this into logarithmic form by changing the base of the exponent to the base of the logarithm. The value of 0.01875 is just the result of dividing 1.5 by 80. We double both sides to isolate t, and use our calculator to determine that the final value is 11.5 days. This is a great example of a question showing a half-life and how we would use it to determine an unknown amount of time. Just really quickly, a reminder that t and p are both measures of time. However, p is a fixed period, which is to say, regardless of where we are on the graph, the p-value would not change. However, t discusses the elapsed time. So that's how much time has passed when we got to a certain value. T is effectively our independent variable of x, and p is a fixed parameter. Here's a worked example regarding half-life that you can try on your own. The only thing I want to mention about this is I want you to note that the start amount was 4.6 grams and the final amount was 1 gram. Notice that the initial amount is larger than the end amount. That's going to be the way it is with half-life because we're decreasing. Also, we'll compare this to our next example where we'll see that rather than talking in the raw values, we'll talk in terms of percentages and see how that changes the question a bit. Good luck with this one. Class example 15 reads as follows. A particular substance is decaying exponentially so that only 10% of the original amount remains after 25.4 hours. Find the half-life of the substance to the nearest tenth. So we know we'll use our growth and decay formula. And here, the first question we're going to ask is, what can we put in as initial and final amounts? We weren't actually told anything about the original mass. However, we were told that at the end, we only had 10% of the original. By default, all things start at 100% of themselves. This means we can put our original amount as being 100 and our final amount as being 10. Now, we could just as easily have put the original amount as being 1, which is the decimal representation of 100%, and put the final amount as being 0.1, the decimal representation of 10%. However, as our first step in this, we'll be dividing both sides by 100, which will achieve that same thing anyway. You'll also note here we've replaced b with 1/2 and then later 0.5. Both of these are equivalent in representing that we're multiplying by half because it's a half-life question. Unlike our previous example though, here we are asked to determine the half-life. That means we don't know the value of p. The 25.4 hours that has elapsed is the t value. Remember, the 25.4, it's not really something that's particular to the half-life of the substance. That's how we know it's not the p-value. At this point, we're trying to get our unknown value of p out of the exponent. This will require us to use logarithms. In this example, it will be easiest for us to convert from power form to logarithmic form by taking the base of 0.5 and making it the base of the logarithm. If we think of a cross multiplication here, we can see that by multiplying both sides by p, we end up with a coefficient of p on the left side, and then in order to isolate that p, we divide both sides by the log base 0.5 of 0.1. This final value will be determined using our calculator, and we find that the half-life of the substance is 7.6 hours. Consider this. To get to 10% of your original amount, if you start at 100 and you were halving, you went from 100% to 50% in the first half-life, from 50% to 25% in the second half-life, from 25% to 12.5% in the third half-life, so you're almost there, and a fourth half-life would take you down to 6.25%. So we're looking for more than 3 and less than 4 half-lives. Well, more than 3 and less than 4 times 7.6 would put us at 25.4 hours. Here's another worked example for you to try on your own. I have two comments to make here. The first, we're using our same growth decay formula, but you'll notice that we don't really see the p-value appear after the initial step. That's because typically when we talk about money or population growth, we refer to the growth in terms of annual rates. So the period is always 1, meaning 1 year, and t is equally measured in years. I also wanted to point out that this one talks about a population increase of 2.1% per year. Recall that 1 is the decimal representation of 100, and so the decimal representation of 2.1% is actually 0.021. You need to divide it by 100. So our b value here is 1 because we maintain the 100% plus 0.021 because that represents the growth. If our population were decaying, we would take 1 and subtract the number, such as 0.021. Here we've shown a graphical solution in addition to the algebraic one, so hopefully you can find your answer two ways. Let's look at a couple more examples of exponential growth by looking at investments where we'll have to work with percentages. So here we're given a mutual fund investment that has earned an average return of 9% annually for several years. We're going to assume that the growth rate stays the same, and we're going to try to determine how long it would take for $5,000 to grow to $12,000, and we'll work this out to the nearest tenth of a year. So here we'll use our growth decay formula, and to determine our b value, we'll take 1, which represents 100%, and we will add 9% to that. Effectively, we're changing 100%, which is an unchanging investment, to 109%, which represents the growth. So this is like taking the amount of $5,000 and multiplying it by 1.09 over and over until it eventually gets to 12,000. Of course, we don't expect it will land exactly on 12,000, so this won't be a sufficient strategy in order to determine the time to the nearest tenth of a year. Instead, we'll set up our equation, replacing the initial amount with 5,000 and the final amount with 12,000. I mentioned earlier that in half-life examples, or any decay example, the a value, which is the coefficient on the right side of the equation, would be larger than the y value, which is the outcome on the left side of the equation. However, here, because we're talking about growth, it'll be the initial value that is smaller and the final amount that is larger. So we're multiplying this by 1.09, and then we have an unknown t, because we don't know how long it will take to get to 12,000. But we know that because our interest rate is annual, there's only one compounding period per year, so our p value is 1. This is an example where our unknown is in the exponent, so we know it'll become a logs question. We start by isolating the power term by dividing both sides by the coefficient of 5,000. And now we can convert this to log form. So 12,000 divided by 5,000 gives us 2.4, and the 1.09 that is the base of the exponent becomes the base of the logarithm. Type this in your calculator, and it turns out to be 10.2 years. Now, let's make this question a little bit trickier. We'll change the rate of return from 9% to 8.8%. That's not much harder. But this time, we'll have the interest compounded monthly. What that means is you get 1/12 of 8.8%, but you get it 12 times per year. Let's see how this changes the question. So this time, instead of adding 0.09 to the 1, we're adding 0.088, but only a 12th of it. So we have to respect the order of operations here and divide the 0.088 by 12 before adding it to the 1. You'll also note that I've changed the p-value now to being 1/12. This is because if we're getting interest each month, a month is 1/12 of a year, and we want our t-value to be in years. Now, some people will approach this differently. They'll leave p as simply being 1, and then their final answer of t will be in months, and they'll convert that to years as the last step. I thought this might be an interesting way to show you a different approach. So let's simplify things a bit. We'll divide both sides by 5,000, and we'll divide t by 1/12, which is the same as saying 12 times t. right? Because dividing by a fraction is like multiplying by its reciprocal. The 1 plus 0.088 over 12, I've left as that expression because it's just going to give us a rather ugly decimal number. And so rather than writing that over and over, I thought I'd write the exact form for you. But you could always work that out first in your calculator and then just use the answer function to use that same value over and over. But you'll notice that that is the base of our power term, and so that converts into the base of the logarithmic term. We find that that logarithmic term evaluates to give 119.8, and so if 12t is equal to 119.8, we can divide both sides by 12, and it turns out that in 9.98 years, which rounds to 10.0 years, we have achieved our $12,000. So notice, we got a slightly lower interest rate, but we actually achieved our goal of $12,000 in less time because of the higher frequency of the interest compounding. Good thing to know. Part C appears the same or similar to Part A and B, but is actually quite a different question. We're told that we have a third fund that grows from $5,000 to $7,605 in 5 years. We're told the interest compounds annually, and we're asked to determine the annual rate of growth correct to the nearest hundredth of a percentage. We're going to use the same growth decay formula. However, this time we replace our initial and final amounts, and we know both the t value and the p value. It took 5 years, and we had an annual compounding, so p is 1. Notice in this question, our unknown is not in the exponent. That means this will not be solved using logarithms. This is the first place students tend to go wrong, is they introduce logarithms unnecessarily here. As a first step, we'll divide both sides by 5,000. At this point, we need to isolate the b. How do we get rid of that power of 5 on a b? Well, it's not with logs. We need to take the fifth root of each side. That's kind of like having an exponent of 1/5. So multiplying 5 by 1/5 would generate an exponent of 1. And putting the left side to 1/5 is like taking the fifth root of it. So we type this in our calculator and we get a number that is 1.0875. And this is the second step where students make a huge error. They were asked to answer to the correct to the nearest hundredth of a percentage. So the reaction is take this 1.0875 number and round it to 1.09. However, 1.0875 is the number we're multiplying by each time, but that's not actually the rate of growth. The rate of growth is the amount that was added to the 100%. So this is like 100% plus 8.75%. And the 8.75% is the average annual growth rate that is the answer to this question. In solving logarithmic equations, we will consider two possible scenarios. Either every single term in the equation will be a logarithmic term. If this is the case, our goal will be to reduce each side to a single term and then chop off the logs, which is to say, undo the same operation on both sides. If, however, any term is not logarithmic, or as we see on the right example, we have one that is constant, then our job will be to put all the logs on the same side, reduce it to a single term, and then convert from a logarithmic to exponential form. In both of these examples, we see how this results in a quadratic equation. Now, the equation you get could be quadratic, it could be linear, it could be other. But what's important is from that point on, after you've solved using the appropriate strategy, you'll still need to check your solutions because it's possible that a solution generates a negative argument or negative base in the original equation. Remember, a logarithmic term cannot have a negative value nor 0 as its base, nor can it have a negative value or 0 as its argument. In the left example, we see that x equals to -1 would have caused a negative argument, and in the rightmost example, we see x equals -2 would have caused a negative argument. But be careful again. It's not enough to just recognize that the number that you had as a solution is negative. We actually have to verify that it creates a negative argument, because in some cases, a positive value could cause a negative argument. In other cases, a negative value could cause a positive argument and therefore not be extraneous. We'll talk about this more in the upcoming example. In class example 17, we'll solve two logarithmic equations, one in which all terms are logarithmic and one in which at least one term is not logarithmic. So in example A, we see a left side of log base 3 of x plus 1 and log base 3 of x added together. Because these two terms have the same base, we'll be able to combine them into a single term by multiplying the arguments. On the right side, we see 1/2 times log base 3 of 144, and so using our log laws, we can raise that coefficient of 1/2 to be an exponent. Recall that an exponent of 1/2 is equivalent to taking the square root of the value, so the square root of 144 gives us 12. And then on the left side, we've multiplied that x plus 1 times x. Here we've written that in the opposite order because it's a little bit easier to write the monomial first. This next step is not really a complicated mathematical one so much as a logical step. If I take the log base 3 of something, and that's equal to the log base 3 of something else, then the something and the something else must be equivalent. So here, the argument of the left side logarithm and the argument of the right side logarithm could be said to be equal. So x times x plus 1 is equal to 12. We multiply the x by x plus 1 to give us x squared plus x. And since it's now a quadratic equation, we default to the strategy of setting it equal to 0 and factoring. Here, since x plus 4 times x minus 3 equals 0, then either x equals negative 4 or x equals positive 3. We must now verify our answers in the original equation. If we replace x with 3, the first argument becomes 4 and the second argument becomes 3. Both of these are positive values. However, if we replace the two x's with negative 4, our first logarithmic term has an argument of negative 3 and the second has an argument of negative 4. In both cases, this is not permissible, and so we must reject this solution as being extraneous. Recall, if ever you check an answer graphically, the graphing calculator will only show answers which are real. That is to say, it will never show you an extraneous root. So, by typing in y1 as our original expression of log base 3 of x plus 1 plus log base 3 of x, and y2 as being 1/2 times log base 3 of 144, we see that the only intersection point on this graph is when x is equal to 3, which is our only solution for the equation. Example B is a similar logarithmic equation, except this time one of our terms is not logarithmic. Notice the 1/2 on the right side of the equation. In this case, our first goal will be to rearrange the equation so that all logarithmic terms are on the same side and all non-logarithmic terms are on the other side. So we will subtract log base 4 of x minus 4 from either side here. Next, we want to combine the two logarithmic terms into a single logarithmic term. In this case, because we have a subtraction of two logarithms, we will write this as a single term with a division of their arguments. So it becomes log base 4 of x plus 2 over x minus 4. The right side has not been changed yet. Now we will convert from logarithmic to exponential form. So the base of 4 of that logarithm will become the base of 4 for our power. So we get 4 to the power of 1/2 is equal to the argument of x plus 2 over x minus 4. And at this point, we'll evaluate 4 to the 1/2 as being the square root of 4, which is 2. In this case, we want to multiply both sides by x minus 4 in order to eliminate any denominators, and then solve for x. We expand the left side, and subtract x from either side and add 8 to either side. This gives us x equals 10. It's important to verify this back in the original expression. Looking at the left side argument, x plus 2 when replaced with 10 gives us a 12. In the right side argument, x minus 4 when x is replaced with 10 gives us a 6. In both cases, these are positive, so this is not an extraneous root. Moreover, by replacing numerically and actually evaluating the left side and right side expression, we can see that they give the same value when 10 is used. One of the motivations for studying logarithmic scales in Math 3-1 is the applications of logarithms in the sciences. In this course, we'll see how logarithms are used in the pH scale, which measures the concentration of hydrogen in a solution, in Richter scales, which measures the intensity of earthquakes, and when measuring the intensity of sound in decibels. When we look at the pH scale as shown in the diagram, what we see is that when we go up or down one step on the scale, we are actually going up by a factor of 10. So if I change from a pH value of 5, which corresponds to black coffee, to a pH value of 4 for tomato juice, I have become 10 times more acidic. If I were to go 2 steps on the scale, going from black coffee to cola now, a 5 to a 3, I have become 10 to the power of 2 times more acidic, so 100 times more acidic. It's important to understand that this is not like a linear scale where we go up by the same amount each time, but rather where we are multiplied by the same amount each time. I'm sure you can connect that in your mind to how an exponential equation is different from a linear one. As we show examples of what these different readings could mean on the Richter scale or the pH scale or decibels, it's important to note that no question in Math 3-1 would ask you to interpret a single reading on a logarithmic scale. Rather, you'll be asked to interpret how one reading relates to another. As an example, if you were asked to compare the intensity of an earthquake measuring 7.1 on a Richter scale to another earthquake measuring 5.3, we could say that the difference in those two values represents the power of 10 times more intense than it is. So, for example, 10 to the 7.1 minus 5.3 evaluates to give 63. That's how many times more intense the larger earthquake would be than the smaller one. Problems involving the decibel scale are really no different from those involving the pH scale or the Richter scale, except for one detail. Typically, we measure sound in decibels, but in order to have these questions work the same as the Richter scale or the pH scale, we would have to work in bels. And this conversion is very simple. I'm sure you can guess that deci means 10, and so we simply divide the value in decibels by 10 to convert it into bels. So, for example, if we were told that an alarm clock sound measured 55 decibels, then we would consider that as 5.5 bels. If we were told that a person whispering was 30 decibels, then we would call it 3.0 bels. After that, comparing the intensity becomes the same matter of subtracting and using as an exponent on 10. So in this example on the page, we see 10 to the 5.5, that's the alarm clock in bels, minus 3.0, the whisper in bels, gives 10 to the 2.5, which is 316 times more intense. Let's use logarithmic scales to compare the intensities of earthquakes. In class example 18, we're given an equation for earthquake intensity, where the intensity is the reference intensity times 10 to the magnitude. We're told that one earthquake measures 5.3 on the Richter scale, and that it's 125 times more intense than a second earthquake, and we're asked to find the magnitude of that second earthquake. So if we just used that single equation, we wouldn't really have enough to solve for anything. We don't know the reference intensity, and we don't actually know the intensity of the first earthquake. However, if we compare the intensity of the larger to the second, we know that that ratio, shown here as I bigger over I smaller, that's equal to a single number, which is 125. If you think about this, it would kind of be like if we were comparing our ages, and you were, say, 20 years old and I was, say, 40 years old. Well, 40 is twice as large as 20, so I would say that I am 2 times older than you. Notice that I've taken your age and my age, but I've put it into a single ratio, that one fraction that has just one number. Similarly here, I bigger over I smaller actually represents just one number, which is the 125. At the same time, because we're comparing the same reference intensity in both cases, that fraction will just reduce to 1, so we don't need to know its numerical value. Because of our exponent laws, we can rewrite 10 to the 5.3 over 10 to the x as 10 to the 5.3 minus x. And with this, we develop an exponential equation with only one unknown. At this point, we can convert from exponential form to logarithmic form because our unknown is in the exponent and solve for x. So we end up with log base 10 of 125 equals 5.3 minus x. Rearrange and evaluate. So we find our answer to be 3.2. Well, that should make sense because if one of them was 100 times more intense, that would be 2 steps higher on the Richter scale, which is to say the 5.3 is 2 units higher than 3.3. So if it's 2.1 higher, then that's 10 to the 2.1, which should be a little bit more than 100, and in this case turns out to be 125 times. Class example 19 is another exploration of logarithmic scales, but this time looking at the intensity of sound. I have to say that I find this question to be a lot more challenging than the previous one in terms of interpretation. However, the solving of it using our strategies is not really that much different. We're told that the loudness of a sound is related to the logarithm of the ratio of the measured intensity. Now, here's where things get tricky. You have to understand the difference between loudness and intensity in this formula, or really just have to understand which numbers are given and what you're looking for. So we're told that during a soccer tournament in 2010, that number will not be used, a noisemaker called the vuvuzela had a measured loudness of 127 decibels. The first thing we'll think about is that we will be working in bells, not in decibels. Now, if you look at the equation that was given to you, that 10 in front of the logarithm, if you were to divide both sides, actually would give us L over 10, which represents the 127 being divided by 10 to turn into 12.7 bells. We're told that the intensity of the sound of the vuvuzela is 5,000 times greater than the intensity of a lawnmower. And we want to know the measured loudness of the lawnmower. All right, well, first, let's recognize that the vuvuzela is louder than the lawnmower. So if we've already determined that 127 is the value of the vuvuzela, the answer should be something smaller. Well, in this case, answers A, B, C, and D are all smaller, so no luck there. So let's recall last time, or from the last problem, that we saw that 10 to the power of the larger magnitude minus the smaller magnitude is actually the ratio of intensity. That means here, if we put the larger one first, which is our 12.7 bells, and subtracted away the smaller one, which is the unknown value of x, that would be equal to a ratio of 5,000. Well, now we have a really easy equation to solve. Exponential with a base of 10 and a single unknown in the exponent. We convert to log form and rearrange to find that x is equal to 12.7 minus log base 10 of 5,000. As we evaluate this in our calculator, we get the number 9.0, and we don't see that anywhere as an answer. But then we recall that that is our answer in bells. So since the question was talking in decibels, we would have to convert that back by multiplying by 10. 9 times 10 is of course 90, and our answer would be C. We can check our answer by putting 10 to the 12.7 minus 9 and finding that the factor of intensity is approximately 5,000 times. I do want to point out that there's another way to do this problem. You'll note you were given an equation, and you're probably wondering why we didn't use it. Well, Because this question wasn't asking about loudness, it was asking for intensity, we would have to, as a first step, rearrange the given formula to solve for I. We would do this by dividing both sides by 10, converting to exponential form, and then multiplying by the reference intensity. At this point, we would have an equation much like we did in class example 18. And much like in 18, we would have to combine two versions of it, which is to say the intensity of the vuvuzela and the intensity of the lawnmower, into a single one by dividing them together. All of this work, though, would just bring us back to that very first step, which was 10 to the bigger minus smaller equals 5,000 times as intense. So it may be a worthwhile algebraic activity for you, but it isn't actually any more productive than just starting as we did here. If you do choose to try it that way, best of luck. And I hope this exploration of logarithms and all their applications has been helpful to you. See you in the next chapter.